Unlocking Microservices Potential, Advanced Architecture and Patterns. Chapter 1, The Ascent to Advanced Microservices. For years, the promise of microservices has resonated deeply within the world of software development. The idea was compelling. Break down monolithic applications into smaller, independent services, each responsible for a specific business capability. This architectural shift promised faster development cycles, the ability to deploy services independently, technological diversity, and the capacity to scale individual components more effectively. Many organizations embarked on this journey, drawn by the allure of agility and resilience. New services were spun up, teams embraced autonomy, and initially, the benefits seemed clear and immediate. However, as these systems matured and scaled, a more nuanced reality began to emerge. The initial excitement often gave way to a growing awareness of significant, often hidden, complexities. What might have started as a manageable handful of services quickly blossomed into dozens, then hundreds, each with its own life cycle, dependencies, and operational quirks. It soon became apparent that simply adopting microservices was one thing, mastering them was an entirely different challenge. The benefits were still there, but they were often buried beneath an unseen iceberg of distributed system problems. This book is about navigating that submerged part of the iceberg. It's about moving beyond the foundational understanding of microservices, the how to build one, to the sophisticated strategies required to build, manage, and evolve highly resilient, performant, and maintainable distributed systems at scale. It's about engineering for the realities of distributed computing, where the network is unreliable, data consistency is a constant battle, and failures are not exceptions but inevitabilities. So, what are these emergent complexities that necessitate an advanced approach? 1. The unpredictability of distributed failures. In a monolith, if one part of the system failed, the whole application might crash, making it easy to diagnose. In a microservices landscape, a single service failure can ripple through the system in unexpected ways, causing cascading failures where one component's instability triggers a chain reaction across dependent services. Services can experience partial failures, where they are technically available but not entirely functional, or suffer from network partitions, where portions of the system become isolated. Pinpointing the root cause in such an intricate web of interactions becomes a form of detective work, demanding specialized tools and patterns to isolate, contain, and recover from these incidents quickly. 2. The conundrum of data consistency. One of the cornerstones of microservices is the database per service pattern, promoting autonomy and reducing contention. While beneficial, this decentralization sacrifices the straightforward atomicity, consistency, isolation, durability, transactions we take for granted in monolithic applications. Suddenly, a single business operation might involve updates across multiple independent databases owned by different services. Achieving strong consistency becomes incredibly challenging, often leading to the adoption of eventual consistency, a state where data will eventually propagate and be consistent, but not immediately. Managing these inconsistencies and ensuring system integrity over time requires careful thought and specialized patterns. 3. The quest for observability. Knowing what's happening within your system is critical. In a monolith, logs and metrics are centralized. In a microservices environment, data points are scattered across many services, machines, and execution environments. Understanding latency, tracing the path of a request across dozens of services, correlating logs, and identifying performance bottlenecks demands advanced strategies for distributed tracing, structured logging, and comprehensive metrics collection. Without these, the system becomes a black box, making debugging and performance optimization nearly impossible. 4. Navigating the security minefield. Every new service, every new communication channel represents a potential attack vector. Securing a microservices architecture means managing authentication and authorization for hundreds of service-to-service interactions, not just user-to-application access. Protecting sensitive data, ensuring secure communication between services, even within the same data center, and managing secrets across a distributed environment adds significant layers of complexity to security considerations. 5. The operational overhead. While microservices promise faster deployments, managing the infrastructure for dozens or hundreds of independent services can lead to significant operational overhead. Deploying, monitoring, scaling, and updating each service, coupled with managing their interdependencies, requires sophisticated automation, robust continuous integration and deployment pipelines, and a shift in how teams operate. 6. Latency and performance at scale. Network communication is inherently slower and less reliable than in-memory communication. As requests traverse multiple services, network hops accumulate, impacting overall request latency. Optimizing communication patterns, reducing chatty interfaces, and efficient data serialization become crucial to maintaining performance. 7. Team coordination and evolution. The architecture of your software often mirrors the communication structure of your organization, a principle known as Conway's Law. While microservices encourage autonomous teams, coordinating changes across service boundaries, managing API versioning, and fostering a culture of shared ownership without creating silos require careful organizational design and cultural shifts. This book aims to provide a practical guide to addressing these challenges head-on. It adopts an advanced mindset, emphasizing proactive engineering and design strategies that anticipate problems rather than reacting to them. We will explore established and emerging patterns, techniques, and tools that empower you to build highly resilient, scalable, and manageable microservices architectures. We will begin by delving deeper into the core challenges of distributed systems, understanding the fundamental problems that all advanced patterns seek to solve. From there, we will explore strategies for engineering resilience and fault tolerance, ensuring your services can withstand the inevitable failures of a distributed environment. We'll then tackle the difficult terrain of advanced data management and the intricacies of distributed transactions, unraveling how to maintain consistency across independent services. The journey continues into the realm of event-driven architectures and event sourcing, transformative patterns for creating highly decoupled and auditable systems. We'll examine the critical infrastructure layers like API gateways and the evolving role of the service mesh in managing communication and cross-cutting concerns. Performance and scalability will be addressed through strategic patterns beyond basic replication. Achieving true insight into your complex system requires mastering the pillars of observability, tracing, logging, and metrics. Finally, we will discuss how to evolve your architecture over time, advanced deployment strategies, and the comprehensive security considerations unique to this landscape. Crucially, we will also explore the human element, how to structure and foster a culture of high-performing teams adapted to the microservices paradigm. The book concludes by looking towards the horizon, considering future trends and the continuous evolution that defines this exciting field. By the end of this book, you will be equipped not just with knowledge of advanced microservices patterns, but with the understanding of why they are needed, when to apply them, and how to implement them to unlock the full potential of your distributed systems. It's time to move beyond the basics and ascend to truly unlocking microservices potential. Chapter 2: Core Challenges in Distributed Systems. Building a microservices architecture means building a distributed system. While the modularity and scalability benefits are undeniable, this transition introduces a fundamental shift in complexity. What was once a relatively straightforward single process running on one machine now becomes a collection of independent processes communicating over a network, often across different machines, data centers, or even continents. This distributed nature comes with a unique set of challenges. Inherent, unavoidable truths about networks and independent components that often surprise developers accustomed to the more predictable world of monolithic applications. To understand why advanced patterns are necessary, we must first grasp these core challenges. They are the problems that every pattern discussed in this book attempts to mitigate, manage, or solve. The fallacies of distributed computing. Decades ago, a group of engineers at Sun Microsystems identified common, yet incorrect, assumptions that developers make when building distributed applications. These are known as the fallacies of distributed computing, and they remain remarkably relevant for microservices architects today. The network is reliable. Networks are inherently unreliable. Cables can be cut, switches can fail, Wi-Fi can drop, and packets can be lost, delayed, or arrive out of order. Assuming perfect network connectivity is a recipe for disaster. Latency is zero. Data does not instantaneously travel from one service to another. Every network hop, every processing step, introduces delay. These accumulated delays can significantly impact application performance and user experience. Bandwidth is infinite. While bandwidth has increased dramatically, it's still a finite resource. Attempting to transfer too much data too frequently can overwhelm network capacity, leading to bottlenecks and degraded performance. The network is secure. A common misconception is that internal networks are inherently safe. In reality, any network, especially one hosting independent services, is susceptible to various security threats, from eavesdropping to unauthorized access. Topology doesn't change. Networks are dynamic. Servers go up and down, IPs change, load balancers reconfigure, and routing paths vary. Services must be prepared to discover and connect to dynamically changing environments. There is one administrator. In a microservices world, different services might be managed by different teams, using different technologies, with different deployment schedules. There is no single point of control, complicating coordination and troubleshooting. Transport cost is zero. Sending data across a network consumes resources CPU cycles for serialization/deserialization, memory for buffers, and actual costs for cloud egress. These costs accumulate at scale. The network is homogeneous. Services might communicate across different network segments, VPNs, or even public internet, using a variety of protocols, REST, gRPC, Kafka, etc. Assuming a uniform network environment simplifies development, but ignores reality. Each of these fallacies highlights a fundamental truth. Anything can go wrong in a distributed system, and you must design your application to account for these eventualities. They frame the why behind the resilience, observability, and security patterns we will explore. Network inevitability, latency, unreliability, and partitions. Beyond the fallacies, other core issues stem from the very nature of network communication. Latency, every call between services, no matter how optimized, incurs network latency. In a chain of 5 microservices, where each call takes just 50 milliseconds, that's 250 milliseconds before any actual processing begins. For user-facing applications, this quickly becomes unacceptable. Designing for asynchronous communication and batching requests becomes critical to minimize this overhead. Partial failures. This is perhaps the most insidious challenge. In a monolithic application, a component either works or it doesn't. In a distributed system, a service might be intermittently slow, unreachable from some clients but not others, or return corrupted data. This is a partial failure. For example, a customer service portal might be able to retrieve customer details but fail to load order history because the order service is experiencing a database timeout. Your system needs to be able to detect, isolate, and respond to these partial failures gracefully, perhaps by degrading functionality or reverting to cached data, rather than crashing the entire user experience. Network partitions. A partition occurs when communication between 2 or more services is impossible within a distributed system. This isn't necessarily a full system crash. It could be a temporary network issue, a faulty router, or a configuration error. During a partition, services on either side of the divide cannot communicate, leading to inconsistency or outright failure if not handled. This directly relates to the CAP theorem, which we'll discuss next. The CAP theorem: consistency, availability, and partition tolerance. The CAP theorem is a foundational concept in distributed computing, stating that a distributed data store cannot simultaneously provide more than 2 out of 3 guarantees. Consistency, C, every read receives the most recent write or an error. All nodes see the same data at the same time. This is akin to strong transactional consistency, ACID. Availability, A. every request receives a non-error response without guarantee that it contains the most recent write. The system is always operational and responsive. Partition tolerance, P. The system continues to operate despite arbitrary message loss or failure of parts of the system. This is a necessity in any realistic distributed system. The network will partition eventually. The CAP theorem essentially says that in the presence of a network partition, which is an inevitability in distributed systems, you must choose between consistency and availability. CP, consistent and partition tolerant. If a partition occurs, the system will prioritize consistency. It might refuse requests or return an error if it cannot guarantee that all services have the latest data. This means sacrificing availability during a partition. Examples include traditional relational databases with strong consistency guarantees or systems like Apache Zookeeper. AP, available and partition tolerant. If a partition occurs, the system will prioritize availability. It will continue to process requests, but there's a risk that different parts of the system might serve stale or inconsistent data until the partition heals. This is often the chosen path for highly available, large-scale web services. Examples include many NoSQL databases designed for high availability, like Cassandra or eventually consistent variants of DynamoDB. Understanding CAP helps guide decisions about data consistency models in microservices. Given that partition tolerance is a necessity, architects primarily choose between strong consistency, sacrificing some availability during partitions, or eventual consistency, prioritizing availability. While traditional strong consistency, ACID, is desirable, it's often impractical and a performance bottleneck across distributed microservices. This leads to the prevalence of eventual consistency models in many modern microservices architectures, which brings its own set of challenges regarding data synchronization across services, a topic we will thoroughly explore. Time and ordering, the clock problem. In a single server, processes share a common clock. In a distributed system, each machine has its own clock, and these clocks can drift. This makes establishing a definitive, global order of events incredibly difficult. If Service A processes an event at 10:01 according to its clock, and Service B processes a related event at 10:00 according to its clock, which event happened first? This clock problem can lead to complex synchronization issues and inconsistent views of system state, especially when dealing with high-volume, time-sensitive operations. Techniques like logical clocks, e.g., Lamport timestamps, vector clocks, or relying purely on event ordering can help, but managing accurate time synchronization and ordering is a significant distributed system hurdle. Concurrency and race conditions. When multiple independent services operate on shared resources or produce side effects that impact each other, you introduce the potential for classic concurrency problems like race conditions. For example, if two services independently try to update the stock level for the same product at the same time, without proper coordination, the final stock count might be incorrect. While database per service helps encapsulate data, business transactions often span multiple services, making sophisticated coordination mechanisms necessary. This is where patterns like the Saga pattern become relevant, managing long-running, compensable transactions across services. The complexity tax. Ultimately, all these challenges culminate in what can be called the complexity tax of distributed systems. Interacting services introduce combinatorial explosion in possible failure modes. Debugging becomes a distributed hunt. Performance optimization requires holistic system-wide analysis. Security cannot be an afterthought. This inherent complexity is why a disciplined, pattern-driven approach is essential. By deeply understanding these core challenges, the fallacies, the inevitability of network issues, the CAP theorem's trade-offs, and the difficulties of time and concurrency, we build the necessary foundation for appreciating and effectively applying the advanced microservices patterns discussed in the following chapters. These patterns are not arbitrary. They are meticulously crafted solutions to these very real and unavoidable problems encountered in a distributed world. Armed with this understanding, we can now move to the engineering strategies that help us build resilience in the face of this inherent complexity. Chapter 3: Engineering for Resilience and Fault Tolerance. In the previous chapter, we explored the unsettling truths of distributed systems. The network is unreliable, failures are partial and inevitable, and consistency is often a trade-off. These realities demand a fundamental shift in how we design our microservices. Instead of aiming for systems that never fail, we must strive for systems that can tolerate failures, recover quickly, and maintain an acceptable level of service even under adverse conditions. This is the essence of resilience engineering and fault tolerance. Resilience is not merely about uptime. It's about a system's ability to absorb change, adapt to failures, and continue to provide value. Fault tolerance is about building mechanisms to ensure that the continued operation of a system is not completely disrupted by faults in its components. Together, they form the cornerstone of robust microservices architectures. Consider a large online retailer. A burst of traffic might slow down their product recommendation service. If not handled correctly, this slowdown could cause the entire website to become unresponsive, leading to lost sales and frustrated customers. A resilient system, however, would detect the recommendation service's degradation, gracefully degrade its functionality, perhaps by showing no recommendations or cached ones, and allow the rest of the site to function normally. Identifying and implementing patterns that enable this kind of graceful behavior is paramount. Let's delve into some of the most critical patterns for achieving resilience and fault tolerance. 1. Circuit breaker pattern. Imagine an electrical circuit breaker in your home. When it detects an overload or short circuit, it trips, disconnecting the power to prevent damage. Once the fault is cleared, you can reset it. The circuit breaker pattern in software works similarly. It prevents a system from repeatedly invoking a failing service, thus avoiding cascading failures and giving the struggling service time to recover. How it works. A circuit breaker acts as a proxy for operations that might fail. It maintains 3 states. Closed, this is the initial state. Calls to the service pass through. If a predefined number of consecutive failures occur, e.g., timeouts, errors, the circuit trips. Open, the circuit is tripped. All subsequent calls to the service are immediately rejected without attempting to call the failing service. This prevents the failing service from being overwhelmed and allows it to recover. After a configurable timeout, e.g., 30 seconds, the circuit transition to half open. Half open, a trial state. A single trial call is allowed to the service. If this call succeeds, the circuit assumes the service has recovered and transitions back to closed. If it fails, it immediately returns to open, restarting the timeout. Benefits: prevents cascading failures, stops a failing service from bringing down its callers and their callers. Faster failure response. Instead of waiting for a timeout, the caller immediately knows the service is unavailable. Provides breathing room, gives the failing service time to recover without being hammered by continuous requests. Considerations: configuration. Sensible thresholds for failures, timeouts, and half-open periods are crucial. Monitoring. It's vital to monitor circuit breaker states to understand system health. Integration. Libraries like Hystrix, though deprecated, its concepts live on in many modern implementations, or Poly for .NET provide ready-to-use implementations. 2. Bulkhead pattern. Following our nautical theme, a bulkhead is a watertight partition in a ship's hull. If one compartment is breached, the bulkheads prevent the entire ship from flooding. In microservices, the bulkhead pattern isolates components, e.g., calls to different external services, different types of requests, into separate pools of limited resources. This ensures that a failure or excessive load in one component does not exhaust resources needed by others, thereby preventing overall system degradation. How it works. You can achieve this by thread pools or connection pools. Allocate distinct, limited thread pools or connection pools for different types of requests or for calls to different downstream services. If one pool is exhausted, only that specific line of communication or a specific feature is affected. Dedicated worker processes. Run critical services or specific functionalities in separate processes or containers, ensuring they have their own isolated resources. Benefits: resource isolation. prevents resource starvation by one misbehaving component. Improved fault isolation. A failure in one area doesn't spread to unrelated parts of the system. Enhanced stability. Allows critical functions to remain operational even if non-critical ones fail. Example, imagine an e-commerce application. Customer logins, payment processing, product catalog display, and recommendation generation are all critical functions. If the recommendation service starts consuming excessive threads or database connections due to a bug or overload, a bulkhead pattern could isolate its resource usage, preventing it from starving resources needed by the customer login or payment services. 3. Retries and timeouts. These patterns often work in conjunction and are fundamental to handling transient network issues or temporary service unavailability. Timeouts. A timeout specifies the maximum duration a calling service will wait for a response from a downstream service. If the response doesn't arrive within this period, the call fails. Without timeouts, a slow or dead service can indefinitely tie up resources in the calling service, leading to resource exhaustion and cascading failures. Timeouts should be applied at multiple layers: network, service client, and perhaps even within the service logic. Retries. A retry mechanism involves reattempting a failed operation. This is incredibly useful for transient failures, like a momentary network glitch, a database deadlock, or a service instance restarting. Considerations for retries. Idempotency is key. Retries should only be applied to idempotent operations, those that produce the same result no matter how many times they are executed, e.g., getting data, setting a value, but not creating a new order unless carefully managed. If an operation is not idempotent, retrying it can lead to unintended side effects, e.g., duplicate orders. Backoff strategy. Simple, immediate retries often exacerbate the problem. An exponential backoff strategy, waiting longer between each retry, is crucial to avoid overwhelming a struggling service. Adding jitter, randomized small variations to the backoff duration, helps prevent all retrying clients from hitting the service at the exact same moment. Max retries. Define a maximum number of retries to prevent indefinite attempts. When to retry, only retry operations where success is possible. Don't retry on permanent errors, e.g., HTTP 400 bad request, HTTP 401 unauthorized. 4. Idempotency. As touched upon with retries, idempotency is a critical property for operations in a distributed system. An idempotent operation is one that can be applied multiple times without changing the result beyond the initial application. How to achieve idempotency. Unique trace IDs/request IDs include a unique identifier with each request. When a service receives a request, it checks if this ID has already been processed. If so, it returns the previous successful response without re-executing the operation. State checks. For operations that modify state, check the current state before applying the change. For example, if you're updating a user's address, check if the address is already the one you're trying to set. Compensable actions. Design operations so that repeated executions don't have cumulative harmful effects. Why it matters. Given the unreliability of networks and the necessity of retries, ensuring idempotency becomes essential for building reliable business processes. Without it, you risk duplicate data entries, double charges, or inconsistent states when messages are redelivered or retried. 5. Graceful degradation and feature toggles. Resilience isn't just about preventing failures, it's also about managing them when they occur. Graceful degradation means that when a part of your system fails or performs poorly, the overall system continues to function, albeit with reduced capabilities or performance. Instead of crashing, it fails gracefully. Techniques for graceful degradation. Fallback mechanisms. If a remote call fails, provide a default or cached response. For instance, if the recommendation service fails, show the most popular items instead of product recommendations. Asynchronous processing. Move non-critical operations to asynchronous queues. If a dependent service is slow, the user-facing process can complete without waiting, while the asynchronous operation can resume when the service recovers. Feature toggles, feature flags. These allow you to turn certain functionalities on or off at runtime without deploying new code. In a crisis, you can quickly disable non-essential, resource-intensive features to reduce load and keep critical services running. This is also invaluable for A/B testing and canary deployments. 6. Rate limiting and throttling. To prevent a single consumer or an overload of requests from overwhelming a service, rate limiting and throttling are employed. Rate limiting restricts the number of requests a client can make to a service within a given time window. Exceeding the limit results in a rejection, e.g., HTTP 429, too many requests. This protects the service from abuse or being swamped. Throttling, similar to rate limiting, but often focused on managing overall load rather than individual client behavior. It may involve queuing requests or applying back pressure when the service is under strain. 7. Chaos engineering, proactively breaking things. Perhaps the most advanced and counterintuitive approach to building resilience is chaos engineering. Instead of waiting for things to break in production, you intentionally inject failures into your system in a controlled manner to uncover weaknesses and build confidence in your system's resilience. Principles of chaos engineering. Form a hypothesis. Start with a specific hypothesis about how the system should behave under failure, e.g., if the payment service becomes unavailable, the checkout flow will degrade gracefully and allow retries later. Vary real-world events. Introduce real-world failures into your system, e.g., network latency, service instance crashes, CPU spikes. Run experiments in production. The most accurate understanding of system behavior comes from experimenting in the production environment, albeit with appropriate safety measures. Automate experiments. Conduct experiments continuously and automatically to catch regressions. Example: Netflix, a pioneer in this field, famously developed tools like Chaos Monkey, which randomly disables instances in their production environment during business hours. This forced their engineers to design services that could cope with disappearing instances, leading to a much more fault-tolerant architecture. By embracing chaos engineering, organizations shift from a reactive, "what do we do when it breaks?" mindset to a proactive, "how do we design it so it can't break in unexpected ways?" approach. Conclusion: engineering for resilience and fault tolerance is not a one-time activity, but an ongoing commitment. It requires a deep understanding of distributed system nuances and a willingness to apply patterns like circuit breakers, bulkheads, intelligent retries, and idempotency, coupled with strategies like graceful degradation and the proactive practice of chaos engineering. These patterns enable services to act as robust participants in a complex ecosystem, minimizing the impact of individual failures and ensuring the overall system remains available and functional, ultimately providing a better experience for the end user. With these foundational patterns in place, we can now turn our attention to the intricate world of data management in a decentralized microservices environment. Chapter 4. Advanced Data Management in Microservices. One of the most profound shifts when moving from a monolithic application to a microservices architecture lies in how data is managed. In a monolith, a single, typically relational, database serves as the centralized store for all application data, ensuring ACID properties, atomicity, consistency, isolation, durability through transactional integrity. This simplifies data consistency, but often becomes a scaling bottleneck and a single point of failure. In a microservices world, this centralized data model is fundamentally challenged by the pursuit of service autonomy and distributed ownership. Each service ideally owns its data, encapsulated within its boundary, inaccessible directly by other services. While this principle simplifies development and deployment within a service, it introduces significant complexities at the architectural level, especially when business processes span multiple services and their respective data stores. This chapter delves into these advanced data management strategies, exploring the patterns and trade-offs required to handle data effectively in a distributed microservices environment. The database per service pattern. The conceptual foundation of data management in microservices is the database per service pattern. This principle dictates that each microservice should own its private database, accessible only by that service. Services communicate via APIs or asynchronous messages, never by directly querying another service's database. Benefits of database per service. Decoupling. Services are truly independent, reducing direct dependencies and allowing teams to choose the best database technology for their specific needs. Polyglot persistence. Scalability. Each service's database can be scaled independently, avoiding bottlenecks. Autonomy. Development teams can manage their database schemas and migrations without coordinating with other teams. Fault isolation. A failure in one database doesn't directly impact others. Challenges introduced by database per service. Distributed transactions. Business processes that involve updating data across multiple services cannot rely on traditional ACID transactions. This is arguably the biggest challenge. Data duplication and consistency. To avoid direct communication for every data lookup, services often need to replicate or denormalize data owned by other services, leading to potential data staleness and consistency issues. Reporting and analytics. Querying data across multiple, disparate databases for aggregate reporting and analytics becomes significantly more complex. Data migrations. Evolving schemas and migrating data, especially when data is replicated, requires careful planning and execution. Tackling data consistency across services. Since traditional two-phase commit, 2PC, or distributed transactions are generally eschewed in microservices due to their blocking nature, performance overhead, and reduced availability, architects must embrace alternative consistency models, primarily eventual consistency. Eventual consistency revisited. As discussed in Chapter 2, eventual consistency means that after a change, data will eventually propagate to all services and become consistent, but there's no guarantee of immediate consistency. In other words, a read might return stale data immediately after a write. Strategies for managing eventual consistency. Callbacks/webhooks. A service that updates its data can notify other interested services by making an API call back to them. This creates tight coupling and requires robust error handling and retry mechanisms. Asynchronous messaging, events, the preferred approach. When a service makes a significant change to its data, e.g., order created, customer address updated, it publishes an event to a message broker, e.g., Kafka, RabbitMQ. Other interested services subscribe to these events and update their local, denormalized copies of the data or trigger subsequent business logic. This provides loose coupling and higher resilience. Pros. Highly decoupled, scalable, durable, allows for replayability of events. Cons. Challenges with ordering, duplicate messages, and ensuring all services process the event successfully. Outbox pattern. A critical pattern to ensure atomic updates between a service's database and its message broker. Instead of directly publishing an event, the event is first recorded in an outbox table within the service's own database transaction. A separate process then reads from this outbox table and publishes the events, guaranteeing that either the database update and the event publication both occur or neither does. Compensating transactions, saga pattern. This pattern is specifically designed to manage long-running business processes that span multiple services and require sequential, yet independent, updates. Instead of an all-or-nothing distributed transaction, a saga is a sequence of local transactions, where each local transaction updates the database of a single service. If a step in the saga fails, compensating transactions are executed to undo the effects of preceding successful transactions, thus bringing the system back to a consistent state. We will explore the saga pattern in detail in Chapter 5. Trade-offs: consistency versus latency versus complexity. Choosing the right consistency model involves critical trade-offs. More immediate consistency often means higher latency, reduced availability due to blocking, and greater complexity in implementation. Embracing eventual consistency allows for higher availability and better performance, but necessitates careful design to handle potential data inconsistencies and provide appropriate user experience feedback, e.g., your order is processing and will be visible shortly. Data synchronization and replication. Many microservices setups require some form of data synchronization or replication to avoid direct queries across service boundaries and to improve performance. Caching. Services often cache data retrieved from other services to reduce network calls and improve response times. This introduces cache invalidation challenges. Strategies include time-to-live, TTL, event-driven invalidation, subscribing to update events, or proactive refresh. Denormalization. Services might hold denormalized copies of data owned by other services to optimize read performance for their specific use cases. For example, an order service might store a copy of the customer name and customer address from the customer service for reporting purposes, even though the customer service is the authoritative source. This requires diligent event-driven updates to keep the denormalized data fresh. Materialized views. For complex queries or reporting purposes that span multiple services, a separate service might maintain a materialized view by subscribing to events from multiple source services and aggregating the data into its own database. This aggregate store can then be optimized for read-heavy analytical queries, decoupled from the transactional databases of individual services. This is a common pattern in CQRS, Command Query Responsibility Segregation architectures, which we'll discuss as part of Chapter 6. Data migration and schema evolution. In a monolithic architecture, a single database schema migration affects the entire application. With service-specific databases, schema evolution becomes a localized concern, but migrating data between services or coordinating schema changes across services that share replicated data introduces new headaches. Strategies for schema evolution. Backward compatibility. Always strive for backward compatible schema changes, e.g., adding nullable columns, new tables. If a breaking change is required, it often necessitates a coordinated rollout of services. Versioned APIs. When a service's API, and thus its data contract, must change in a non-backward compatible way, provide versioned APIs, e.g., v1 users, v2 users, to allow consumers to gradually migrate. Double writes and reads. For major data refactoring or migrations, a double write pattern can be used. During a transition period, a service writes data to both the old and new schema database. Reads can then be directed to either, allowing for verification, and once confidence is gained, reads are switched entirely to the new schema, and the old one is deprecated. Event-sourced migrations. In event-sourced systems, discussed in Chapter 6, schema evolution can sometimes be simpler, as raw events are immutable. Projections, materialized views, can be rebuilt from the event stream with a new schema. Reporting and analytics. The distributed nature of data in microservices poses significant challenges for traditional reporting and business intelligence. Buy tools that expect a single, centralized database. Approaches for reporting. Dedicated reporting database data warehouse. A common pattern is to create a separate reporting microservice or data warehouse that consumes events from various operational services, transforms them, and aggregates them into a schema optimized for analytical queries. This creates a highly denormalized, read-optimized store where buy tools can operate without impacting transactional services. GraphQL or API aggregation. For some real-time, lightweight reporting needs, an API gateway or a dedicated query service might aggregate data by making calls to multiple microservices. This can suffer from latency issues for complex queries. Data lake event stream processing. For truly massive-scale analytics, feeding all raw events from microservices into a data lake, e.g., S3, HDFS, and applying stream processing or batch analytics, e.g., Spark, Flink, is an increasingly popular approach. Conclusion: data management in microservices is fundamentally different and inherently more complex than in monolithic systems. Embracing the database per service pattern means accepting the challenges of distributed transactions, eventual consistency, and fragmented data views. However, by strategically applying patterns like event-driven architectures, the outbox pattern, and carefully designed compensating transactions, sagas, along with techniques for data synchronization and robust schema evolution, organizations can effectively manage their data, achieve high service autonomy, and build resilient, scalable microservices architectures. This foundational understanding sets the stage for delving deeper into specific patterns like sagas and event-driven architectures in the subsequent chapters. Chapter 5. Tackling Distributed Transactions, the Saga Pattern and Beyond. In Chapter 4, we established that one of the most significant challenges in advanced microservices architectures is managing data consistency across multiple, independent services. The traditional atomic acid, atomicity, consistency, isolation, durability transactions, which guarantee all-or-nothing operations within a single database, are simply not practical or desirable across service boundaries in a distributed system. Attempting to use them would lead to high latency, reduced availability, and tightly coupled services, undoing many of the benefits of microservices. So, how do we handle business processes that inherently involve multiple services, where failure at any step requires complex coordination or reversal of previous actions? This is where the concept of distributed transactions comes in, reimagined for the microservices world. The primary solution for managing these is the Saga pattern. The problem with distributed transactions, 2PC and its woes. Before diving into sagas, it's worth briefly understanding why traditional distributed transactions, often implemented using the two-phase commit, 2PC protocol, are typically avoided in microservices. Blocking operations. 2PC is a blocking protocol. Participants, databases, services hold locks on resources for the entire duration of the transaction, impacting concurrency and throughput. Performance overhead. The coordination messages between a transaction coordinator and multiple participants add significant network latency. Single point of failure. If the transaction coordinator fails, the entire distributed transaction can be left in an uncertain state, potentially leading to data inconsistencies. Tight coupling. It couples services too tightly, as they must all agree on the outcome of a single transaction. Given these drawbacks, the mantra in microservices is often, avoid distributed transactions. But business processes often are distributed. This is where the Saga pattern shines. The Saga pattern, a sequence of local transactions. The Saga pattern is a way to manage distributed transactions by sequencing a series of local transactions, where each local transaction updates the database of a single service. If a local transaction fails, the Saga executes compensating transactions to undo the changes made by preceding successful local transactions, thereby maintaining data consistency. Think of it like booking a complex trip. Book flight, local transaction 1. Book hotel, local transaction 2. Rent car, local transaction 3. If booking the car fails, you need to compensate by canceling the hotel and canceling the flight. This is the essence of a Saga. Key characteristics of a Saga. Each step, local transaction, is typically an independent ACID transaction within its service. Each step involves sending an event or command to the next service in the sequence. If a step fails, compensation steps are executed for all previously completed steps. Saga orchestration versus choreography. There are two main ways to implement the Saga pattern, each with its own advantages and disadvantages. 1. Choreography-based Saga. In a choreography-based Saga, there is no central orchestrator. Each service involved in the Saga publishes events upon completing its local transaction. Other services subscribe to these events and perform their own local transactions in response. How it works. Service A starts the Saga by performing its local transaction and publishing an event, e.g., order created. Service B subscribes to order created, performs its local transaction, and publishes its own event, e.g., payment processed. Service C subscribes to payment processed, performs its local transaction, and publishes inventory reserved. If any service fails its local transaction, it publishes a failure event, e.g., payment failed, which then triggers compensation logic in previous services. Example, order creation. Order service creates an order as pending, publishes order created event. Payment service subscribes to order created event, charges customer. If successful, publishes payment processed event. If failed, publishes payment failed event. Inventory service subscribes to payment processed event, decrements inventory. If successful, publishes inventory reserved event. If failed, publishes inventory failed event. Order service, again, subscribes to inventory reserved event to set order status to approved. Subscribes to payment failed event or inventory failed event to set order status to canceled and trigger compensation on previously successful steps. Pros: loose coupling. Services are highly independent, no central point of control. Simpler for small sagas, can be easier to implement for sagas with few steps. Decentralized decision-making. Each service decides its own behavior based on events. Cons: complexity for large sagas. As the number of steps grows, it becomes very difficult to track the overall flow, understand dependencies, and manage compensation logic, the spaghetti code problem of events. Debugging and monitoring. Hard to pinpoint where a saga has failed or stalled without specialized tools. Cyclic dependencies. Risk of introducing cyclic dependencies if services subscribe to each other's failure events. 2. Orchestration-based saga. In an orchestration-based saga, a central saga orchestrator, often itself a service, is responsible for managing the state of the saga and directing each participant service to perform its local transaction. The orchestrator sends commands to participants and subscribes to their response events. How it works. A client initiates the saga by sending a request to the orchestrator. The orchestrator sends a command to Service A. Service A performs its local transaction and sends a reply event back to the orchestrator. Based on Service A's reply, the orchestrator sends a command to Service B, and so on. If a service reports failure, the orchestrator issues commands to previous services to execute their compensating transactions. Example: order creation. Order service receives customer request, sends a command, e.g., create order command to order orchestrator. Order orchestrator receives create order command. Saves saga state, e.g., creatordrpndng. Sends process payment command to payment service. Payment service processes payment. Sends payment processed event or payment failed event to order orchestrator. Order orchestrator, if payment processed event, updates saga state, paymentcomplete, sends reserve inventory command to inventory service. If payment failed event, updates saga state, paymentfaled, sends cancel order command to order service. This is a compensating transaction. Inventory service reserves inventory, sends inventory reserved event or inventory failed event to order orchestrator. Order orchestrator, if inventory reserved event, updates saga state, invntoryrservd, sends complete order command to order service. Saga complete, if inventory failed event, updates saga state, invntorYFALED, sends rollback payment command to payment service, compensation for payment, then sends cancel order command to order service. Pros: clear separation of concerns. Business logic for coordination is centralized in the orchestrator. Easier to understand and debug. The flow of the saga is explicitly defined. Better error handling. Orchestrator knows the overall state and can manage compensation more effectively. Less coupling. Services are unaware of each other's existence, only communicating with the orchestrator. Cons: potential single point of failure bottleneck. The orchestrator becomes critical. Mitigated by making the orchestrator itself highly available and scalable. Added complexity. Requires building and maintaining the orchestrator logic. Service-specific commands. The orchestrator needs to know the specific commands for each service. Practical considerations for sagas. Regardless of whether you choose choreography or orchestration, several practical considerations apply. Communication mechanism. Reliable asynchronous messaging, e.g., Kafka, RabbitMQ, is crucial. Messages must be delivered at least once, and services must be idempotent to handle duplicate messages. Idempotency of transactions. Every local transaction, and especially every compensating transaction, must be idempotent. Retriggering a compensation step must not have unintended side effects. Monitoring and observability. Sagas are long-running and distributed. You need robust distributed tracing and logging to track the progress of a saga instance and quickly identify failures. Timeouts and retries. Build in timeouts for each step of the saga. The orchestrator, or participating services in choreography, needs retry logic with exponential backoff for commands that fail due to transient issues. Human intervention. For complex sagas or unhandled failures, mechanisms for human intervention, e.g., alerts, manual workflow tools, might be necessary to resolve issues that cannot be automatically compensated. Outbox pattern revisited. To ensure atomicity between a service's local database transaction and publishing an event, which might kick off the next saga step or a compensation, the outbox pattern discussed in Chapter 4 is critical. This ensures that the local transaction is committed and the event is published or neither happens. Beyond sagas, alternative approaches. While sagas are the most prominent advanced pattern for distributed transactions, a few other concepts are worth mentioning. Try confirm cancel (TCC) pattern. Similar to sagas, TCC involves 3 phases for each participant. Try, reserve resources and prepare for the action, ensuring executability. Confirm, execute the action if all participants successfully try. Cancel, release reserved resources if any participant fails the try phase, acting as a compensation. This pattern offers a stronger consistency guarantee within a transaction, but requires participants to implement the specific try, confirm, cancel interfaces. Many modern microservices libraries and frameworks offer specific saga orchestration engines, e.g., Temporal, Cadence, Apache Camel, that abstract much of this complexity, allowing developers to focus on the business logic rather than the plumbing. Conclusion: tackling distributed transactions is a quintessential advanced microservices challenge. By abandoning the problematic 2-phase commit and embracing the saga pattern, architects can design long-running business processes that span multiple services while maintaining eventual consistency and system resilience. The choice between choreography and orchestration depends on factors like saga complexity, team structure, and desired debuggability. Regardless of the choice, strong messaging infrastructure, careful error handling, and robust observability are paramount. With sagas as a core tool, we empower our microservices to collaborate effectively on complex business workflows, laying a solid foundation for building truly robust and flexible distributed applications. This understanding now opens the door to exploring how event-driven architectures can further enhance decoupling and data flow within our advanced microservices ecosystem. Chapter 6. Event-driven architectures and event sourcing. In the journey toward advanced microservices, one concept repeatedly surfaces as a powerful enabler of decoupling, scalability, and resilience: events. Instead of services communicating primarily through direct requests, event-driven architectures, EDA, center around services publishing and consuming events. This chapter delves into the transformative power of EDAs, their benefits, and 2 key patterns that often complement them: event sourcing and command query responsibility segregation, CQRS. The power of events. An event is a significant occurrence or change of state within a system. It's a statement of fact about something that has happened. For example, order created, payment processed, customer address updated, shipment dispatched. The beauty of events lies in their immutability and their nature as notifications. A service publishes an event without knowing or caring who might consume it. Any interested service can subscribe to that event and react accordingly. This leads to profound decoupling. Benefits of event-driven architectures: loose coupling. Services don't need to know about each other's existence or implementation details. They only need to agree on the format of events. This makes services much easier to develop, deploy, and evolve independently. Scalability. Event producers and consumers can scale independently. A message broker, e.g., Kafka, RabbitMQ buffers events, allowing consumers to process them at their own pace. If a particular service is under heavy load, it can process events more slowly without impacting the upstream producers. Resilience. The intermediary message broker provides durability. If a consumer service goes down, events accumulate in the broker and are processed once the service recovers. This prevents data loss and cascading failures. Real-time processing. Events enable real-time reactions to changes in the system. As soon as an event occurs, interested consumers can react, facilitating real-time data flows and dynamic user experiences. Auditability and replayability. Events, being immutable records of facts, create a natural audit log of everything that happened in the system. This historical record can be invaluable for debugging, analytics, and even for replaying events to build new projections or recover state. Extensibility. Adding new functionalities often means simply adding new event consumers without modifying existing services. This allows for easier system extension and experimentation. Challenges of event-driven architectures. Complexity. Event flows can be harder to understand and debug than traditional request-response interactions, especially without robust tooling for distributed tracing and event monitoring. Eventual consistency. EDAs inherently lead to eventual consistency as consumers process events at their own pace. This requires careful design to ensure the user experience handles potential data staleness. Event schema management. Evolving event schemas while maintaining backward and forward compatibility can be challenging. Data duplication. Services often duplicate data locally from events published by other services, leading to consistency management issues if not handled carefully. Event sourcing, storing state as a sequence of events. Traditional databases store the current state of an entity. When an entity changes, its existing record is updated, and the previous state is lost. Event sourcing flips this model. Instead of storing the current state, it stores every change to an entity as an immutable sequence of events. The current state is then derived by replaying these events. How it works. Command. A request comes in to change the state of an entity, e.g., create order, add order item. Validation. The system validates the command against the current state, derived from replaying past events for that entity. Event generation. If valid, one or more new events are generated, e.g., order created, order item added. These events describe the change that has occurred. Event persistence. These new events are appended to an event store, an append-only log. This is the only source of truth for the entity's state. State projection. The current state of the entity is not directly stored, but is built by applying all historical events in sequence. For read-heavy applications, these projections can be materialized into read models, e.g., in a traditional database for efficient querying. Benefits of event sourcing. Full history audit log. You have a complete, temporal record of every change that ever happened. This is invaluable for auditing, debugging, and understanding business processes over time. Temporal querying. You can reconstruct the state of an entity at any point in time by replaying events up to that point. This is powerful for historical analysis, debugging, and business intelligence. Simplified data models. The event store is simple, just append events. Complex relationships can be defined in the projections. Resilience and durability. Events are immutable facts stored in an append-only log, making them highly durable. Facilitates event-driven architecture. Event sourcing naturally generates the events needed for an event-driven architecture, making it easier to integrate with other services via a publish-subscribe model. Challenges of event sourcing. Complexity. It's a significant paradigm shift and can be harder to implement and reason about initially. Querying the event store. Querying the raw event store for the current state can be inefficient for complex reads. This necessitates the use of projections or read models. Event schema evolution. Changing the schema of past events is extremely difficult as they are immutable. Techniques like upcasters or migrators are needed to transform old event formats into new ones during replay. Debugging. Understanding the state of an entity requires rehydrating it from events, which can be computationally intensive and mentally taxing. Compensating transactions. While event sourcing provides an audit trail, correcting or undoing past events often requires emitting new compensating events rather than deleting or modifying historical ones. Command Query Responsibility Segregation, CQRS. CQRS is an architectural pattern that separates the model used to update information, the command side, from the model used to read information, the query side. This separation allows for independent optimization, scaling, and evolving of read and write workloads. CQRS is often used with event sourcing, as the event store provides a natural write model, and projections become the read models. How it works: command-side write model handles commands, requests to change state, validates commands and executes business logic, generates and publishes events, especially if combined with event sourcing, updates the durable write store, e.g., event store or a traditional database optimized for writes. Query-side read model handles queries, requests to retrieve data, reads from a separate, possibly denormalized, read-optimized data store. This read store is updated by consuming events published by the command side. Example: consider an e-commerce platform. Command side: when a customer places an order, a create order command is processed. This updates the transactional database, or event store, and publishes order created event. Query side: a dashboard displaying live orders would query a dedicated, denormalized read model. This read model is populated by subscribing to order created event and subsequent events like payment processed event, shipment dispatched event to update its state. Benefits of CQRS: independent scaling. Read and write models can be scaled independently based on their respective load profiles. Read models can be widely replicated and optimized for querying, while write models can be optimized for transactional integrity. Optimized models: each model can be designed for its specific purpose. The write model can be optimized for complex business logic and transactional integrity, while the read model can be optimized for queries and reporting performance, e.g., using different database technologies, denormalized schemas. Improved performance: reads, especially complex ones, can be very fast as they query a dedicated, potentially highly denormalized store. Flexibility and evolution: different teams can work on and evolve the read and write models independently. Integration with event sourcing: CQRS is a natural fit for event sourcing, where the event store is the write model and the projections are the read models. Challenges of CQRS: complexity. CQRS introduces a significant increase in architectural complexity. You now have two distinct models to manage, along with the propagation mechanism between them. Eventual consistency: the read model will inherently be eventually consistent with the write model. This implies that a read immediately after a write might not show the very latest state. Data synchronization: ensuring reliable and efficient synchronization between the write and read models via events requires robust messaging, idempotent consumers, and error handling. Event streaming platforms: the backbone of EDAs. Modern event-driven architectures often rely on sophisticated event streaming platforms like Apache Kafka. These platforms provide a persistent, fault-tolerant, and high-throughput way to publish, subscribe to, and store events. Key features of event streaming platforms: publish-subscribe model, decouples producers from consumers. Durability and persistence: events are stored for a configurable period, allowing consumers to process them even after outages or to replay historical events. Scalability: horizontal scaling for both producers and consumers. Ordering guarantees: ensures events are processed in the order they were produced within a partition. Stream processing: many platforms integrate with stream processing frameworks, e.g., Kafka Streams, Apache Flink, that allow for real-time aggregation, transformation, and analysis of event streams. Conclusion: event-driven architectures, especially when combined with event sourcing and CQRS, represent a fundamental shift in how we design and build microservices. They prioritize decoupling, scalability, and resilience by making events the first-class citizens of our systems. While they introduce significant architectural complexity, the benefits in terms of flexibility, auditability, and independent scaling often outweigh the challenges for complex, evolving software systems. Understanding these powerful patterns and their associated trade-offs is crucial for building truly advanced microservices that can adapt and thrive in dynamic business environments. With these foundations, we can now turn our attention to the critical infrastructure layer that manages communication, discovery, and observation across our distributed services. Chapter 7: API Gateways, Backend for Frontends, and Service Mesh. As microservices grow in number and complexity, the ways in which they expose their functionality and interact with each other become critical. Managing communication, routing, security, and observability across dozens or hundreds of independent services requires dedicated infrastructure layers. This chapter explores three essential components that address these concerns: the API gateway, the backend for frontends, BFF, pattern, and the service mesh 1 API gateways, the entry point to your microservices. An API gateway acts as a single, intelligent entry point for all client requests into your microservices ecosystem. Instead of clients making direct calls to individual microservices, which could be numerous, and their locations might change, they route all requests through the API gateway. The gateway then intelligently routes these requests to the appropriate backend services. Key responsibilities and benefits of an API gateway: request routing maps incoming requests to the correct internal microservice. This decouples clients from the internal topology of your services. Authentication and authorization centralizes security concerns. The gateway can handle authentication, e.g., validating JWT tokens, and then pass security context to downstream services, or even make authorization decisions itself. Rate limiting and throttling controls the traffic load on your microservices, protecting them from abuse or overload by limiting the number of requests from specific clients or over certain time periods. Response aggregation. For complex screens that require data from multiple microservices, the gateway can aggregate responses from several backend services into a single response before returning it to the client. This reduces network round trips for the client. Protocol translation can translate between external protocols, e.g., HTTP REST, and internal ones, e.g., gRPC Kafka. Load balancing distributes incoming requests across multiple instances of a microservice. Caching can cache responses for frequently requested data, reducing the load on backend services and improving response times. Logging and monitoring centralizes logging and metrics collection for all incoming requests, providing a single point of observation. API versioning can manage different versions of your API, directing requests to the appropriate service version. Considerations for API gateways. Complexity. An API gateway can become a complex, critical component. Over-engineering it can lead to a new monolithic bottleneck. Performance. All traffic flows through it, so its performance is paramount. Deployment needs to be highly available and scalable. Single point of failure. While it's a single point of entry, it needs to be designed for high availability to avoid becoming a single point of failure. Popular API gateway solutions include Spring Cloud Gateway, Netflix Zool, now part of Spring Cloud Netflix, though less active, NGINX, Kong, and various cloud provider offerings, e.g., AWS API Gateway, Azure API Management, Google Cloud Endpoints. 2. Backend for frontends, BFF, pattern. While a general-purpose API gateway handles common cross-cutting concerns, it often cannot perfectly cater to the diverse needs of different client applications, e.g., a web application, an iOS app, an Android app. This is where the backend for frontends, BFF, pattern comes into play. The BFF pattern suggests creating a separate API gateway or a dedicated microservice, specifically for each client type, or sometimes even for distinct views within a single client. How it works. Instead of client single API gateway microservices, you have client type A BFF for a microservices and client type B BFF for B microservices. Each BFF is optimized for its specific client's user experience, UX, and data requirements. For example, a web BFF might aggregate data into a rich HTML view, while a mobile BFF might send a lighter JSON payload optimized for cellular networks. Benefits of the BFF pattern. Client-specific optimization. APIs can be tailored to the exact needs of each UI, avoiding overfetching or underfetching of data. This improves client performance and simplifies client development. Decoupling client and backend. Changes to a specific client's API don't necessarily impact other clients or the underlying microservices. Reduced client-side complexity. Clients receive pre-aggregated and transformed data, reducing the need for complex data manipulation on the client side. Team autonomy. front-end teams can have direct control over their respective BFFs, allowing them to rapidly iterate on their user interfaces without waiting for a generic API team. Considerations: increased number of services, introduces more services to manage, potential for duplication. Some common aggregation or transformation logic might be duplicated across multiple BFFs. Consistency, ensuring consistency in data formats where necessary across different BFFs can be a challenge. 3. Service mesh, inter-service communication reimagined. While API gateways handle external client-to-service communication, the service mesh addresses the complexities of inter-service communication within the microservices ecosystem. It's an infrastructure layer that handles communication between services, offloading common concerns from the application code. How it works: the sidecar proxy. The core of a service mesh is typically a sidecar proxy. This is a lightweight network proxy, e.g., Envoy, that runs alongside each service instance, often in the same Kubernetes pod. All inbound and outbound network traffic for a service is intercepted and routed through its local sidecar proxy. The sidecar proxy then performs a variety of functions, managed and configured by a central control plane, e.g., Istio's Pilot, Mixer, Citadel components. The application service itself remains unaware that its traffic is being routed through the proxy. Key capabilities and benefits of a service mesh: traffic management, traffic routing, fine-grained control over how requests are routed, e.g., A/B testing, canary deployments, splitting traffic across service versions. Load balancing, sophisticated algorithms for distributing traffic across service instances. Retries and timeouts, automatically handles retries with backoff and enforces timeouts at the network level, offloading this logic from application code. Circuit breaking, implements automatic circuit breaking to prevent cascading failures. Security, mutual TLS, MTLS, automatically encrypts and authenticates all service-to-service communication, ensuring that only trusted services can communicate. Access control, enforces granular access policies based on identity, service, or request attributes. Observability, distributed tracing, automatically collects trace data for requests as they hop across multiple services, providing deep visibility into latency and bottlenecks. Metrics collection, gathers detailed metrics, e.g., request volume, latency, error rates for all service communications. Logging, provides centralized logging for network interactions. Resilience, builds in resilience patterns directly into the infrastructure layer, making the application code simpler and more focused on business logic. Policy enforcement, allows setting and enforcing policies for communication, such as request limits and quotas. Why a service mesh? V's library's API gateway. Language agnostic. Because it runs as a sidecar proxy, it works with services written in any language, unlike client-side libraries, e.g., Netflix Hystrix, Ribbon. Centralized control. A central control plane allows for unified configuration and policy enforcement across a large and diverse microservices landscape. Separation of concerns. Network resilience, security, and observability are offloaded from developers to the infrastructure, allowing developers to focus on business features. Reduced boilerplate code. Developers don't need to implement circuit breakers, retries, or MTLS in every service. Considerations for service mesh. Complexity. Introducing a service mesh adds a significant layer of infrastructure to manage and debug. It has its own learning curve. Overhead. The sidecar proxies introduce some CPU and memory overhead, though typically minimal. Increased latency. An extra network hop for each service call through the proxy adds a slight increase in latency. Not a silver bullet. It solves network concerns, but still requires application-level resilience, data management, and business logic. Popular service mesh implementations include Istio, Linkerd, and Console Connect. The interplay. These three components, API Gateway, BFF, and Service Mesh, are not mutually exclusive. They often complement each other. API Gateway handles traffic from external clients into the service ecosystem. BFF provides a client-specific API layer that sits behind the API gateway or sometimes replaces it for specific clients. Service Mesh manages internal service-to-service communication, handling network concerns without requiring direct application code changes. Together, they form a robust communication and infrastructure layer that offloads cross-cutting concerns from your individual microservices, making them simpler, more focused, and easier to manage at scale. With this critical infrastructure in place, our attention now shifts to optimizing the performance and scalability of the services themselves. Chapter 8. Strategic Patterns for Scalability and Performance. Building a microservices architecture often begins with the promise of enhanced scalability, the ability to scale individual components independently rather than the entire monolithic application is a foundational benefit. However, achieving true, advanced scalability and peak performance in a distributed environment goes far beyond simply adding more instances. It requires strategic design choices, careful optimization of communication patterns, and intelligent resource management. This chapter delves into key patterns and considerations for optimizing the scalability and performance of your microservices, moving beyond basic load balancing to more sophisticated techniques. 1. Advanced load balancing and traffic distribution. While API gateways and service meshes provide foundational load balancing, strategic configuration can further optimize performance. Intelligent load balancing algorithms. Beyond simple round-robin, explore algorithms like least connection directs new requests to the server with the fewest active connections. Least response time sends requests to the server that is currently responding fastest. Weighted round-robin least connection assigns different weights to servers based on capacity or performance, sending more traffic to stronger servers. Sticky sessions, session affinity. In some cases, you might want a client's subsequent requests to go to the same service instance. While generally avoided in true stateless microservices, as it negatively impacts elasticity, it can be necessary for certain legacy integrations or specific session-based designs. Ensure it's used only when absolutely necessary and configured carefully to avoid creating hotspots. Geographic load balancing, global server load balancing, GSLB. For global deployments, GSLB directs user traffic to the geographically closest data center or region, significantly reducing latency. This requires managing multiple deployment points and considering data synchronization across regions. 2. Effective caching strategies. Caching is perhaps the most effective way to improve performance and reduce database load. In a microservices environment, caching becomes more complex due to distributed nature and data consistency challenges. Cache placement, in-process caching, cache data within the service's memory. Fastest but limited by memory, and data is lost if the instance restarts. Only suitable for read-heavy, less frequently changing data. Distributed caching, e.g., Redis, memcached, a separate dedicated cache layer accessible by multiple service instances. Provides shared, fault-tolerant caching that scales horizontally. More network overhead than in process, but offers greater consistency and availability. Cache invalidation. This is the harder part. Time to live, TTL, data expires after a set period. Simple but can lead to stale data if the source changes before TTL expires. Event-driven invalidation. When the source data is changed, the owning service publishes an event, e.g., product price updated. Cache consumers subscribe to these events and invalidate or update their cached entries. This is the most robust method for maintaining consistency, but requires a sophisticated eventing system. Write through, write back. Data is written to the cache and then synchronized with the primary data store, write through, or buffered in the cache and then written to the primary store, write back. Cache granularity. Cache at the write level entire pages, API responses, or just specific data objects. Overcaching can lead to high memory consumption and complex invalidation logic. 3. Data sharding and partitioning for extreme scale. When a single database or data store cannot handle the volume of data or throughput of read-write operations, sharding or partitioning becomes necessary. This involves horizontally scaling a database by splitting its data across multiple independent physical instances. Horizontal partitioning, sharding, how it works. divides data rows into distinct logical groups, and each group is stored in a separate database instance, shard. For example, customer data could be sharded by custom range or orders by order date. Sharding key. The chosen field used to distribute data across shards, e.g., customer ID, tenant ID. Choosing an effective sharding key is critical to ensure even distribution and minimize cross-shard queries. Benefits. Enables massive scalability beyond the limits of a single server, improves performance by reducing the dataset size per query, and enhances fault tolerance. A shard failure only affects a subset of data. Challenges. Increased operational complexity. Resharding, resizing, or adding shards is extremely difficult, and managing queries that span multiple shards can be complex. Vertical partitioning. Divides a table into multiple tables based on columns, or functionally splits a database into multiple databases. This is often the first step towards database per service. Functional partitioning. Each microservice has its own database, making the service boundary the natural data partition. This is the ultimate goal of database per service. 4. Asynchronous communication patterns for throughput. Synchronous, request-response communication, like REST over HTTP, is convenient, but can limit scalability and throughput, especially when services have varying response times or prone to transient delays. Asynchronous communication patterns, primarily based on message queues and streaming platforms, are crucial for high-performance microservices. Message queues, e.g., RabbitMQ, SQS, Azure Service Bus. How it works. A producer sends a message to a queue and doesn't wait for a response. A consumer pulls messages from the queue at its own pace. Benefits. Decoupling, improved responsiveness, producer doesn't wait, load leveling, sudden spikes are buffered by the queue, and increased throughput. Use cases. Background processing, e.g., email sending, image resizing, long-running workflows integrating disparate systems. Stream processing, e.g., Kafka Kinesis. How it works. Similar to message queues, but provides ordered, durable storage of events, logs of changes, that can be read by multiple consumers, potentially many times. Benefits. Enables real-time analytics, event sourcing, complex event processing, and facilitates data pipelines for reporting and integration. Use cases. Real-time data streams, audit logging, complex event processing, change data capture. Key performance considerations for asynchronous systems. Idempotency. Consumers must be designed to handle duplicate messages. Error handling and dead letter queues, DLQS. Mechanisms to handle messages that cannot be processed successfully to prevent them from blocking the queue. Throughput versus latency. Asynchronous communication often improves overall system throughput, but can introduce higher individual message latency from producer to consumer. 5. Performance optimization at the service boundary. Beyond architectural patterns, granular optimization within and between services can significantly impact performance. Efficient data serialization. JSON XML. Human-readable but can be verbose, leading to larger payloads and more processing time. Binary protocols, e.g., gRPC/protobuf, Avro, Thrift. More compact, faster to serialize/deserialize, and strictly typed, making them excellent choices for high-performance inter-service communication. Payload optimization. Avoid overfetching. Only retrieve the data fields that are absolutely necessary. GraphQL can be beneficial here by allowing clients to specify their data requirements precisely. Compression. Use HTTP compression, gzip, Brotli for large payloads. Database query optimization. Even with database per service, individual service database queries must be efficient. Proper indexing, query tuning, and avoiding N+1 queries are critical. Connection pooling. Maintain pools of database and service connections to avoid the overhead of establishing new connections for every request. Thread pool management. Configure thread pools for message consumers and request handlers to optimize resource utilization and prevent overload. Batching throttling external calls. Grouping requests to external systems, e.g., third-party APIs, into batches can reduce network round trips and improve efficiency. Implement careful throttling to avoid overwhelming external services. Conclusion: scalability and performance are not just features. They are non-functional requirements that must be baked into the design of advanced microservices from the outset. By strategically employing advanced load balancing, intelligent caching, methodical data partitioning, and embracing asynchronous communication, you can build systems capable of handling immense loads and delivering rapid responses. Coupled with fine-grained performance optimization within each service, these patterns ensure that your microservices architecture can truly live up to its promise of elastic, high-performing applications. With our systems now optimized for speed and scale, the next logical step is to ensure we can clearly see and understand their behavior: observability. Chapter 9: The Pillars of Observability. Tracing, logging, and metrics. As microservices proliferate, the complexity of understanding what's happening within your system skyrockets. In a monolithic application, you inspect logs, monitor a few key metrics, and perhaps attach a debugger. In a distributed microservices ecosystem, a single user request can traverse a dozen or more independent services, each running on a different machine, potentially in different technologies. When something goes wrong or performance degrades, pinpointing the root cause becomes akin to finding a needle in a haystack spread across 1,000 different fields. This is where observability becomes not just a nice-to-have, but an absolute necessity. Observability is the ability to infer the internal state of a system by examining its external outputs. For microservices, these outputs typically fall into three core pillars: tracing, logging, and metrics. Together, they provide the comprehensive insight needed to debug, optimize, and operate complex distributed systems effectively. 1. Distributed tracing. Following the request's journey, imagine a user reports that their order failed. In a monolith, you might check a single log file. In microservices, the order failed event might involve the order service, payment service, inventory service, notification service, and a shipping service, all communicating asynchronously. Distributed tracing allows you to visualize the entire life cycle of a request as it flows through multiple services. How it works: each incoming request is assigned a unique trace ID. This trace ID is then propagated to every downstream service call made during the processing of that request. Each step or operation within a service generates a span, which represents a unit of work, e.g., an HTTP call, a database query, a specific function execution. The span contains information like its unique ID, its parent span ID, linking it to the preceding operation, the service name and operation name, start and end timestamps, metadata tags, logs, error information. All these spans are collected and sent to a centralized tracing system, e.g., Jaeger, Zipkin, Tempo. This system then stitches together the spans using their trace and parent IDs to reconstruct the full end-to-end flow of the request, often visualizing it as a waterfall or flame graph. Benefits of distributed tracing. Root cause analysis. Quickly identify which service failed or introduced latency in a complex transaction. Performance optimization. Pinpoint performance bottlenecks across service boundaries, e.g., discover that service B is slow, not service A. Dependency mapping. Understand the true runtime dependencies between services. Error blame assignment. Clearly see which service is responsible for an error reported by a client. Implementation considerations. Tracing context propagation, the most crucial aspect. Ensure trace IDs are seamlessly propagated through all communication channels, HTTP headers, message queues, gRPC metadata. Sampling. For high-volume systems, 100% tracing can be resource-intensive. Intelligent sampling strategies, e.g., always trace errors, sample a percentage of normal requests, are common. Open standards. Embrace open standards like open tracing or open telemetry to ensure vendor neutrality and interoperability. 2. Advanced logging, contextualizing events. Logging is the oldest form of observability, but in microservices, it needs to evolve beyond simple text files. Each service generates its own log data, and correlating events across these disparate sources is challenging. Key principles for advanced logging: structured logging. instead of plain text, log in a structured format, typically JSON. This makes logs machine-readable and easily parsable. Each log entry should contain key-value pairs for critical attributes like timestamp, service name, severity, message, user ID, requested, and crucially, the trace ID from distributed tracing. Log aggregation. With logs coming from hundreds of independent services, a centralized log aggregation system is paramount, e.g., ElkStack, Elasticsearch, Logstash, Kibana, Grafana Loki, Splunk. This allows you to search, filter, and analyze logs from all services in one place. Contextual logging. Inject relevant context into log messages. For instance, if processing an order, include the order ID in all related log entries. This makes diagnosis much easier. Appropriate logging levels. Use logging levels, debug, info, warn, error, fatal, effectively to control verbosity and prioritize critical information. Avoid sensitive data. Be mindful not to log sensitive information, PII, credentials. Benefits of advanced logging. Detailed incident investigation. Provides granular details about events leading up to and during an incident. Auditing and compliance. Offers a historical record of system activity. Business insights. Can be mined for operational or business intelligence, e.g., tracking feature usage. 3 comprehensive metrics. Quantifying system health. Metrics are numerical measurements that describe how a system is behaving over time. While logs provide discrete events, metrics offer aggregated, quantifiable insights into resource utilization, performance, and error rates. Types of metrics. Service level metrics. Request rate, error rate, latency response times, average, P95, P99, throughput. Resource metrics. CPU utilization, memory usage, disk I/O, network I/O per service instance. Business metrics. Specific to your application's domain, e.g., orders placed per minute, users signed up, payment conversion rate. Custom metrics. Anything else you deem important for your application, e.g., cache hit ratio, number of messages in a queue. Key principles for metrics. Standardized naming. Use consistent naming conventions across all services to make dashboards and alerts easier to configure. Tagging labeling. Attach meaningful labels, e.g., service name, host, environment, and point name, to metrics to allow for powerful filtering and aggregation. High cardinality issues. Be mindful of adding too many unique labels, which can lead to cardinality explosion and overwhelm your metrics system. Centralized collection. Use dedicated metrics collection agents, e.g., Prometheus, Datadog agents, and a centralized time series database, e.g., Prometheus, Graphite, InfluxDB for storage and querying. Benefits of comprehensive metrics. Proactive monitoring and alerting. Detect anomalies and potential issues before they impact users. Performance trends. Identify long-term performance degradation or improvements. Capacity planning. Understand resource consumption and plan for scaling. SLA, SLO tracking. Measure adherence to service-level agreements objectives. Dashboarding. Create visual representations of system health for engineers and operations teams. Observability in practice. From data to actionable insight. Collecting tracing, logging, and metrics data is only the first step. The true value comes from aggregating, visualizing, and analyzing this data to drive operational decisions. Integrated dashboards. Tools like Grafana or specialized observability platforms allow you to combine metrics, logs, and traces on a single dashboard, providing a holistic view of your system. For example, a dashboard could show the latency of a service, metric, link to specific traces for slow requests, and display relevant log messages. Alerting and anomaly detection. Configure alerts on key metrics and log patterns. Go beyond simple threshold-based alerts to incorporate anomaly detection, which can identify deviations from normal behavior. Runbooks and automated response. When an alert fires, have clear runbooks, step-by-step guides for engineers. For recurring issues, consider automating remedial actions. Chaos engineering integration. As discussed in Chapter 3, chaos engineering benefits immensely from robust observability. You need to clearly see the impact of injected failures to validate hypotheses about system resilience. Conclusion. Observability is the nervous system of an advanced microservices architecture. Without robust distributed tracing, structured logging, and comprehensive metrics, your microservice ecosystem becomes a black box, making it impossible to effectively debug problems, optimize performance, or proactively manage system health. Investing in the right tools and practices for observability is not an overhead. It's a critical enabler for the successful operation and evolution of scalable, resilient distributed systems. With this deep insight into our systems, we can now move to how to strategically evolve these architectures over time and deploy changes safely and continuously. Chapter 10: Evolutionary Architecture and Advanced Deployment Strategies. Building an advanced microservices architecture is not a one-time project. It's a continuous journey. Requirements change, technologies evolve, and business needs shift. The architecture itself must be designed to adapt and grow over time without requiring constant, costly rewrites. This concept is central to evolutionary architecture. Coupled with this mindset are advanced deployment strategies that enable rapid, low-risk changes, ensuring continuous delivery and constant improvement. Evolutionary architecture. Design for chain. Coined by Rebecca Parsons, Neil Ford, and Patrick Kua, evolutionary architecture defines an architecture that supports guided, incremental change across multiple dimensions. In the context of microservices, this means building systems that can evolve gracefully without major disruptions. Key principles of evolutionary architecture for microservices: fitness functions, architectural guardrails. Treat architectural characteristics, like scalability, security, performance, maintainability, as testable objectives, called fitness functions. These can be automated tests, e.g., performance benchmarks, static code analysis for security vulnerabilities, or manual checks, e.g., peer reviews for maintainability. Fitness functions guide the architecture's evolution, ensuring that changes don't inadvertently degrade critical properties. For example, a latency fitness function ensures that no new service or change introduces excessive overhead. Incrementality. Designed for small, continuous changes rather than large, infrequent ones. Microservices naturally support this by allowing individual services to evolve independently. Break down larger features or architectural changes into small, deployable increments. Manage change. Embrace change as an inherent part of software development. Plan for it, don't resist it. Foster adaptive planning and continuous learning loops. Loose coupling and high cohesion. These are fundamental to microservices and vital for evolutionary architecture. Loose coupling minimizes ripple effects when a service changes. High cohesion means a service does one thing well, making it easier to understand and modify. Polyglot persistence and programming. The freedom to choose the right technology for the right job, e.g., a graph database for relationships, a NoSQL store for key value data within service boundaries, facilitates evolution. Teams aren't locked into a single technology stack. Automated testing and deployment. Robust continuous integration, continuous delivery, CI/CD pipelines are non-negotiable. They provide the necessary safety net and speed for frequent, reliable deployments. Advanced deployment strategies. Safe, rapid releases. The ability to deploy changes frequently and with high confidence is a hallmark of successful microservices adoption. Advanced deployment strategies minimize risk by progressively exposing new code to production traffic. 1 blue-green deployments. How it works: maintain 2 identical production environments. Blue, the current live version, and green, the new version. When deploying a new version, services are deployed to the green environment, thoroughly tested there, and then all traffic is instantly switched from blue to green at the load balancer or API gateway. If something goes wrong, traffic can be instantly rolled back to blue. Benefits: near zero downtime, fast rollback, confidence in deployment. Challenges: resource-intensive, requires twice the infrastructure, potential difficulties with stateful services or database migrations. For services with database per service, managing database migrations carefully is crucial during the switchover. 2 canary releases. How it works: deploy a new version of a service to a small subset of production servers, diverting a small percentage of live user traffic, e.g., 1 to 5% to it. Monitor the canary version closely for errors, performance degradation, or unexpected behavior. If the canary performs well, gradually roll out the new version to more servers until it replaces the old one. If issues arise, immediately roll back to the old version. Benefits: reduced risk exposure, only a small segment of users affected, early detection of issues with live traffic, allows for A/B testing variations. Challenges: requires sophisticated traffic routing, often handled by a service mesh or advanced load balancer. Robust monitoring to detect subtle problems, and careful management of data consistency if the canary might make irreversible changes. 3 feature flags, feature toggles. How it works: decouple code deployment from feature release. Features are developed and deployed to production, but remain dark, disabled, until explicitly turned on via a configuration setting, the feature flag. This allows code to be deployed frequently without impacting users. Benefits: continuous deployment. Developers can integrate and deploy code changes multiple times a day. Instant rollback. If a feature causes issues, it can be disabled instantly without a new deployment. A/B testing and gradual rollouts. Easily roll out features to specific user segments. Reduced merge conflicts. Smaller, more frequent merges. Implementation requires a feature flagging service, e.g., launch darkly, optimizely, or a custom solution to manage flag states and provide real-time updates to services. Challenges: can introduce complexity into the codebase if flags are managed poorly. Technical debt in the form of old, unused flags must be regularly cleaned up. 4 dark launches, shadowing. How it works: send a portion of live production traffic to a new version of a service, but the new version's responses are not returned to the user. Its output is simply observed or compared with the current live version. This allows assessment of performance, reliability, and correctness under real production load without risking user impact. Benefits: risk-free live environment testing, allows for side-by-side comparison with the current version, identifies potential performance bottlenecks or correctness issues before real users are affected. Challenges: requires infrastructure to mirror traffic, can increase cost due to dual processing, and doesn't test the impact on the client side. Managing data schema evolution and API versioning. With distributed services owning their data, evolving schemas and APIs is more complex than in a monolith. Data schema evolution. Backward compatibility. Prioritize backward compatible changes, e.g., adding nullable columns, adding new tables. Consumers can then continue to use the old schema, and the new schema supports the new features. Migration tools. Use database migration tools, e.g., Flyway, Liquibase per service. Double write read strategy. For non-backward compatible changes, temporarily write to both old and new schema variants. Gradually switch reads from old to new, then remove old schema. This requires careful coordination. Event sourcing benefits. If using event sourcing, Chapter 6, changing the schema of projections is easier, as the raw events, source of truth, are immutable. Upcasters can translate old event formats to new ones during replay. API versioning, URL versioning, v1 users, v2 users, simple and explicit. Header versioning, e.g., accept. Applications/vndmyipv1 plus JSON, cleaner URLs, but requires client to manage headers. Content negotiation, less common for major version changes, but useful for minor format variations. Evolutionary design, Postal's law/robustness principle. For minor changes, prefer additive changes, adding new fields, and be liberal in what you accept from clients, while being conservative in what you send. This minimizes the need for hard versioning. Deprecation strategy. Clearly communicate API deprecation policies and provide ample time for consumers to migrate to newer versions. Run monitoring to identify clients still using deprecated versions. Conclusion: evolutionary architecture and advanced deployment strategies are symbiotic in the world of microservices, designing for change through fitness functions, incrementality, and loose coupling, while simultaneously enabling safe, rapid releases through blue-green, canary, and feature flags, creates an incredibly agile and resilient development and operations environment. This approach allows organizations to continuously innovate, adapt to new market demands, and maintain competitive advantage without being constrained by a rigid, unchanging architecture. With our architecture now designed to evolve and deploy with confidence, we must now consider how to protect this sophisticated landscape from malicious threats. Chapter 11. Securing your advanced microservices landscape. Security in a microservices architecture is fundamentally different from a monolithic application. While a monolith typically presents a single, well-defined perimeter for defense, microservices distribute functionality across numerous, interconnected services. This creates a much larger attack surface, with many more network endpoints, communication channels, and data stores to secure. The complexity scales with the number of services, making a holistic, layered security approach essential. This chapter delves into comprehensive security considerations unique to microservices, covering everything from identity and access management to data protection and compliance. 1. Identity and access management, IAM, for users and services. Security fundamentally relies on establishing who or what is accessing resources and what they are authorized to do. In microservices, this applies not only to end users, but also to the services themselves. User identity and authentication. Centralized identity provider, IDP. Use a dedicated external, e.g., Auth0, Okta, Azure AD B2C, or internal, e.g., Keycloak, identity provider to manage user authentication. Services should delegate authentication to this IDP. JSON Web Tokens, JWTs. After successful authentication, the IDP issues a JWT. This token contains claims about the user, e.g., user ID, roles, permissions. JWTs are stateless and can be passed from the client through the API gateway to downstream services. Services can then validate the JWT signature to ensure its authenticity and integrity. User authorization. Role-based access control, RBAC. Assign roles to users, e.g., admin, customer, editor, and define permissions based on these roles. Attribute-based access control, ABAC. More fine-grained authorization based on attributes of the user, resource, or environment, e.g., user can only access documents where region matches user region. Policy enforcement points. Authorization checks should occur at the API gateway for coarse-grained checks and at the service boundary for fine-grained, resource-specific checks. Services should never implicitly trust claims from upstream. Service-to-service authentication and authorization. Mutual TLS, MTLS. As discussed in Chapter 7, a service mesh can enforce MTLS for all inter-service communication. This ensures that every service authenticates the identity of the service it's communicating with and encrypts all traffic. It significantly reduces the attack surface from within the network perimeter. Token-based authentication, internal. For services outside the mesh or when MTLS is not fully implemented, services can use short-lived, centrally managed tokens, e.g., OAuth 2.0 client credentials flow, signed JWTs, to authenticate with each other. This is superior to static API keys. Principle of least privilege. Each service should only have the minimum necessary permissions to perform its function. Map permissions to specific roles or responsibilities. 2. API security best practices. The API gateway is often the first line of defense for external threats. API gateways as enforcement points. Centralize authentication, authorization, rate limiting, and input validation at the gateway. This protects backend services from malformed or malicious requests. Input validation and sanitization. Every service must validate and sanitize all incoming data, whether from an external client or another internal service. Never trust input. This prevents common attacks like SQL injection, cross-site scripting XSS, and command injection. Rate limiting and throttling. Prevent denial of service, DoS, attacks and brute force attempts by limiting the number of requests clients or services can make within a time frame. Secure communication, TLS/SSL. All communication, both external to internal and internal to internal, should be encrypted using strong TLS/SSL protocols. API versioning. Use consistent API versioning, as discussed in Chapter 10, to manage changes securely without breaking existing clients. Cross-origin resource sharing, CORS. Properly configure CORS policies to control which origins are allowed to make requests to your API. 3. Data encryption in transit and at rest. Data protection is crucial for both security and compliance. Encryption in transit. Encrypt all data as it moves across networks using TLS/SSL or MTLS. This prevents eavesdropping and tampering. Encryption at rest. Encrypt data stored in databases, file systems, and backups. Most cloud providers offer built-in encryption for data stores. For highly sensitive data, consider application-level encryption, where data is encrypted before it's written to the database. Key management. Securely manage encryption keys using hardware security modules, HSMS, or key management services, KMS, provided by cloud providers, e.g., AWS KMS, Azure Key Vault, Google Cloud KMS. 4. Secrets management. Credentials, API keys, database passwords, and private keys are secrets. Hard-coding them or storing them in environment variables is highly insecure. Dedicated secrets management service. Use a centralized secrets management service, e.g., HashiCorp Vault, AWS Secrets Manager, Kubernetes secrets with external integration, to store, distribute, and rotate secrets securely. Dynamic secrets. Wherever possible, use systems that provide dynamic, short-lived credentials, e.g., an IAM role for a service to access a database rather than static secrets. Regular rotation. Rotate secrets frequently to minimize the window of exposure if a secret is compromised. 5. Microservices-specific security challenges and solutions. Vulnerability management. Each service dependencies need to be scanned regularly for known vulnerabilities. Automate this process in your CI/CD pipeline. Supply chain security. Be aware of open-source and third-party libraries. Use tools to analyze dependencies for vulnerabilities. Container security. If using containers, ensure container images are built securely, minimal base image, regularly scanned for vulnerabilities, and run with appropriate security contexts. Network segmentation. Implement strong network segmentation, e.g., VLANs, subnets, network ACLS, Kubernetes network policies, to isolate services from each other. Limit communication to only what is absolutely necessary. Sidecar security. If using a service mesh, the sidecar proxy itself is a potential attack vector. Ensure the sidecar proxy is up-to-date and securely configured. Security logging and monitoring. Aggregate security-relevant logs, authentication failures, authorization rejections, suspicious activity into a centralized security information and event management (SIEM) system. Set up alerts for anomalous behavior. 6. Compliance and data privacy. With data distributed across multiple services and potentially across different geographical regions, meeting compliance requirements, e.g., GDPR, HIPAA, PCI DSS, becomes more complex. Data locality. Understand where your data resides and process it accordingly to meet regulatory requirements around data residency. Data classification. Classify data by sensitivity level and apply appropriate security controls. Consent management. Implement robust mechanisms for user consent for data collection and processing. Right-to-be-forgotten data portability. Design your services to handle requests for data deletion or export efficiently across all relevant services. Privacy by design. Incorporate privacy considerations from the very beginning of the design process, not as an afterthought. Conclusion. Securing an advanced microservices architecture is an ongoing, multifaceted endeavor that requires a shift from perimeter defense to a deeper, layered security in-depth strategy. It's not about finding one magical solution, but rather about weaving security into every layer of the architecture. From identity and access control to network segmentation, data encryption, and robust secrets management. By adopting these comprehensive security practices, organizations can confidently build and operate scalable, resilient, and secure microservices systems, while also ensuring compliance with stringent regulatory requirements. With the technical architecture now robustly secured, the final piece of the puzzle is the human element: how to build and empower the teams that will successfully deliver and operate these complex systems. Chapter 12. Building high-performing microservices, teams, and culture. So far, our discussions have largely centered on the technical aspects of advanced microservices, patterns, tools, and architectural decisions. However, perhaps the most critical factor for microservices success isn't technological, but organizational and cultural. Microservices aren't just a technical architecture, they are an organizational one. The way teams are structured, how they communicate, and the culture they embody directly impact the effectiveness and health of a microservices landscape. This chapter explores the profound link between organizational design and microservices success, focusing on how to build high-performing teams and cultivate a culture conducive to distributed systems. Conway's Law, the inevitable alignment. In 1968, Melvin Conway proposed an enduring principle: organizations which design systems are constrained to produce designs which are copies of the communication structures of these organizations. This is Conway's Law. In the context of microservices, Conway's Law suggests that if you have a monolithic team structure, e.g., a single large team responsible for one giant application, you are likely to end up with a monolithic application. Conversely, to truly leverage microservices, you need organizational structures that can build and own independent services. This means moving away from functional silos, e.g., a single QA team, a single ops team, a single backend team, to cross-functional product teams. Autonomous, cross-functional teams. The ideal organizational unit for microservices is the autonomous, cross-functional team. Autonomy. These teams are largely independent. They have ownership over a specific set of microservices, or a business domain, and possess the authority to make decisions about their architecture, technology stack, development practices, and deployment schedules. This fosters innovation and speeds up decision-making. Cross-functional. Each team contains all the skills necessary to deliver its services end-to-end. Developers, quality assurance, operations engineers, product owners, and sometimes even UX designers. This reduces handoffs, improves communication, and builds shared understanding and ownership. Benefits of autonomous teams. Faster time to market. Teams can iterate and deploy more frequently without external dependencies slowing them down. Increased ownership and accountability. Teams are responsible for the entire lifecycle of their services, from development to production operation. Improved quality. Closer collaboration within the team leads to better understanding of requirements and potential issues. Higher developer satisfaction. Teams feel empowered and engaged. Challenges of autonomous teams. Homogeneity versus diversity. Striking a balance between allowing polyglot technologies for team expertise and problem fit, and maintaining a degree of consistency for easier maintenance and talent mobility. Duplication of effort. Teams might inadvertently re-implement common functionalities, e.g., logging, authentication helpers. Ensuring architectural consistency. Without centralized governance, architectural patterns might diverge significantly, making cross-service collaboration or system-level changes difficult. Knowledge silos. Specific expertise might be concentrated within teams, making it hard to share knowledge broadly. You build it, you run it culture. A natural extension of team autonomy and cross-functionality is the you build it, you run it philosophy, popularized by Amazon and Netflix. This means the same team that develops a microservice is also responsible for its operation and production, including monitoring, incident response, and on-call duties. Benefits. Increased quality and reliability. Developers instinctively write better code and implement robust testing and monitoring when they know they will be paged if something breaks at 3 a.m. Faster feedback loops. Operations feedback directly informs development decisions, leading to continuous improvement. Reduced friction. Eliminates throwing code over the wall to a separate operations team. Improved operational knowledge. Developers gain invaluable insights into how their services perform in real-world scenarios. Challenges. On-call burden can lead to burnout if not managed properly, e.g., fair rotation, adequate tool support, reasonable incident volume. Skills gap. Development teams might initially lack operational expertise. Investment in training and DevOps tooling is crucial. Tooling investment requires robust CI/CD pipelines, automated testing, comprehensive observability tools, and self-service infrastructure, fostering collaboration and shared understanding. While autonomy is key, teams within a microservices ecosystem are part of a larger whole. Collaboration and shared understanding are vital to prevent fragmentation and foster system coherence. Internal open source, inner source, treat internal shared components or libraries like open source projects. Teams can contribute to and improve common utilities, reducing duplication. This involves shared ownership. Components are openly available, with contributions encouraged from across the organization. Clear governance. Define contribution guidelines, review processes, and clear maintainers. Discovery. Make it easy for teams to discover existing components. Community of practice, COPI guilds, create informal groups of individuals with shared interests, e.g., a front-end guild, an observability COPI, a database best practices guild. These cross-team groups facilitate knowledge sharing, best practice dissemination, and help drive architectural consistency without imposing top-down mandates. API design guidelines and standards. Establish clear guidelines for API design, res-TFL principles, error handling, versioning to ensure consistency and ease of integration across services. These should be collaboratively developed and iterated upon. Shared infrastructure teams. While application teams are autonomous, highly specialized infrastructure concerns, e.g., Kubernetes platform, centralized logging, service mesh operations, can be owned by dedicated platform teams. These teams build paved roads or self-service platforms that enable application teams to move quickly and efficiently, adopting best practices by default. Leadership challenges in a distributed development effort. Leading an organization, transitioning to or operating in a microservices model, requires a shift in leadership style. Empowerment and trust. Leaders must trust their autonomous teams and empower them to make decisions. Micromanagement is detrimental. Clear vision and North Star. While teams have autonomy, leadership must provide a clear overall product vision and strategic direction to ensure all efforts align towards common business goals. Cultural transformation. Managers must actively champion the cultural shift towards ownership, continuous improvement, and learning from failure. Investment in enablement. Leaders must prioritize investment in tooling, training, and platform teams that enable autonomous teams to succeed. Managing dependencies and coordination when necessary. While services are meant to be independent, major, cross-cutting features or architectural shifts still require coordination. Leadership's role might involve facilitating communication, identifying inter-team dependencies early, and resolving conflicts. For instance, sometimes a scrum of scrums or similar forum can help. Dealing with failure. Foster a culture where failures, which are inevitable in distributed systems, are viewed as learning opportunities, not blame opportunities. Conclusion. The success of an advanced microservices architecture is inextricably linked to the organizational design and culture that surrounds it. Building autonomous, cross-functional teams, empowering them with a you build it, you run it mandate, and fostering a culture of collaboration through inner source, guilds, and consistent API practices are paramount. This cultural transformation, guided by supportive and visionary leadership, creates an environment where microservices can truly deliver on their promise of agility, scalability, and innovation. With robust teams and culture in place, we can now briefly look ahead to the future trends that will continue to shape the microservices landscape. Chapter 13, The Horizon, Future Trends, and Continuous Evolution. We have journeyed through the intricate landscape of advanced microservices, dissecting their core challenges, exploring patterns for resilience, managing complex data, optimizing communication, ensuring observability, enabling continuous evolution, and securing these distributed ecosystems. We also examine the critical role of organizational culture and team dynamics. As we conclude this expedition, it's vital to acknowledge that the world of software architecture is dynamic and ever-evolving. The patterns and tools discussed in this book provide a robust foundation, but the horizon is constantly shifting. This final chapter touches upon emerging trends and concepts that are likely to shape the next generation of microservices architectures, emphasizing the importance of continuous learning and adaptation. One, serverless computing and function as a service, FaaS. The evolution towards smaller, more granular operational units beyond microservices often leads to serverless computing and function as a service, FaaS. Instead of deploying long-running services, developers deploy individual functions, e.g., AWS Lambda, Azure Functions, Google Cloud Functions, that are event-triggered, scale instantly, and incur costs only when executed. Intersection with microservices, nanoservices, FaaS can be seen as an extreme form of microservices focusing on single-purpose functions. Event-driven nature. FaaS and serverless platforms are inherently event-driven, aligning perfectly with the principles discussed in Chapter 6. Reduced operational overhead. Much of the infrastructure management is abstracted away by the cloud provider, reducing the you build it, you run it burden on teams. Challenges to consider: vendor lock-in, strong ties to specific cloud provider ecosystems. Cold starts, initial latency when a function hasn't been recently invoked. Debugging and observability. Can be challenging to trace complex workflows across many tiny, ephemeral functions. Cost management. While often cheaper at low scale, costs can surprisingly escalate at high scale if not managed carefully. Distributed complexity remains. Even if individual functions are simple, coordinating across many can reintroduce the distributed system complexities we've discussed. Serverless doesn't replace traditional microservices entirely, but extends the toolkit, offering optimal solutions for specific use cases, e.g., event processing, webhook handlers, batch jobs. Large systems might increasingly become a hybrid of traditional microservices and serverless functions. 2. WebAssembly, WASM, beyond the browser. WebAssembly, WASM, is a binary instruction format for a stack-based virtual machine. While initially designed for web browsers, its potential extends far beyond. WASM runtimes are becoming increasingly efficient and secure, offering a compelling alternative for running code outside of containers or traditional virtual machines. Potential impact on microservices. Universal runtime. WASM's ability to run code written in multiple languages, Rust, Go, C++, etc., with near-native performance in a sandboxed environment makes it attractive for highly efficient, portable microservices. Faster cold starts for FaaS. WASM modules are much smaller and faster to load than typical container images, potentially mitigating the cold start problem in serverless functions. Edge computing. WASM's small footprint and fast start times make it ideal for deploying application logic closer to data sources and users, reducing latency. Enhanced security. The WASI, WebAssembly System Interface standard provides a secure, capability-based model for module interaction with the host system, offering a strong isolation boundary. While still nascent, WASM could significantly impact how lightweight, high-performance microservices are built and deployed in the coming years. 3. Artificial intelligence and machine learning in operations, AI Ops. As microservices environments become too complex for humans to manage manually, AI Ops, artificial intelligence for IT operations, is gaining traction. AI Ops platforms leverage AI and ML to analyze large volumes of operational data, logs, metrics, traces, to automate IT operations. Role in advanced microservices, anomaly detection. ML algorithms can learn normal system behavior and rapidly detect deviations that indicate potential issues, often before they impact users. Root cause analysis. Automate the correlation of events, logs, and metrics across services to pinpoint the root cause of an incident more quickly than human engineers. Predictive maintenance. Predict potential failures based on historical data patterns. Automated remediation. trigger automated responses or self-healing actions based on detected issues. Noise reduction, filter out irrelevant alerts, reducing alert fatigue for on-call teams. AI ops tools promise to make the operational burden of vast microservices landscapes more manageable, turning raw observability data into actionable insights and automated responses. 4. Continued evolution of the service mesh. The service mesh is evolving rapidly, moving beyond basic traffic management to become a critical control plane for the entire distributed system. API gateway convergence. Some service mesh implementations are starting to absorb API gateway functionalities, effectively becoming the single entry point for both external and internal traffic. Policy enforcement. Greater integration with security and compliance policies, allowing granular control over data flow and access. WASM integration. Running WASM modules directly within proxy sidecars to enable custom logic, e.g., data transformation, advanced filtering, without recompiling the proxy itself. Beyond Kubernetes. While heavily associated with Kubernetes, service mesh concepts are expanding to other environments, including virtual machines and bare metal. 5. Data mesh and decentralized data governance. As organizations embrace the data is product mentality, the data mesh paradigm builds on microservices principles for data. It advocates for decentralized data ownership, treating analytical data similar to operational services owned by domain teams, accessed via well-defined APIs, and emphasizing data as a product. This inherently impacts how microservices interact with and contribute to an organization's overall data landscape for analytics and AI. Continuous adaptation. The only constant, the rapid pace of innovation, dictates that the most valuable skill for any architect or engineer in the microservices space is the ability to continuously learn and adapt. The patterns and technologies discussed in this book provide a strong conceptual framework, but their specific implementations and optimal applications will continue to evolve. Key takeaways for staying ahead: embrace experimentation. Don't be afraid to try new technologies and patterns on smaller, less critical parts of your system. Stay informed. Follow industry leaders, research emerging trends, and participate in communities of practice. Focus on principles, not just tools. While tools change, the underlying principles of distributed systems, resilience, and good software design remain constant. Feedback loops. Continuously solicit feedback from operations, development, and business stakeholders to evolve your architecture to meet changing needs. The journey into advanced microservices architectures is challenging, rewarding, and never truly finished. It demands technical prowess, an adaptive mindset, and a commitment to continuous improvement. By embracing the principles outlined in this book and staying curious about what the future holds, you are well positioned to unlock the full potential of your microservices and build systems that are not only powerful and resilient, but also capable of evolving with the dynamic demands of the digital age.